All right, so we're going to review over simplifying square roots. And normally, I'm okay with you splitting into like a perfect square and a prime number, or a number that's the product of two prime numbers. But we're going to do factor trees, which takes the guesswork out of it. And also, it helps you for when we do like cube roots and fourth roots and fifth roots. Because let's face it, like we might be really good at identifying a perfect square, but we're not really good at identifying a number that's like a perfect fourth. Okay? So, we're going to do several without a variable, and then we'll do several of them with a variable. And on every single problem, we're going to do a factor tree. Okay? So 108, I can split that into 2 and 54. And then 54, that will split into 2 times 27. And 27 is 3 times 9. 3 is prime. And then 9 is 3 times 3. All right, so I like to write at the bottom what I have here. So I have 2 to the second, and then I have 3 to the third. So here's the thing. When I am working with my square roots, okay, we're going to end up with 3 of them here. These powers, the ones that are perfect squares, will be even numbers, because what number is right here in this little crook? A 2. This is a 2. And whenever we put a number underneath there, like say for instance I've got the 2 squared, I take that power and I divide it by the root number. So this actually, if it's going to divide, it would be an even number, would be a perfect square, right, to divide evenly. So if I look at 3 to the third, 3 is not going to divide by the 2 on the outside. So I have to think, okay, well, what is the biggest number that is smaller than 3 that will divide by 2? And that would be 2. So I'm going to use 2 of them here, because that's going to make a perfect square. And then the one that I'm not using as a perfect square will represent my prime number that's underneath the root. So the prime numbers will always stay underneath. So when I take and square root this, this is the same thing as saying 2 to the 2 divided by 2, right? Power divided by root number. Times, this is the same thing here. 3 to the power divided by the root number. And then the square root of 3 is the prime number, and that's always the one that stays under the root. So this would actually be 2 to the first power, right? And this would be 3 to the first. So 2 times 3 is 6, square roots of 3. I have now reduced this root. Okay, so this is its simplest form. Now, if we do it like I would normally do it, and how we'll do it later on, you need to think about a perfect square and a prime number that will multiply together to make 108, and that would actually be 36 and 3. And the square root of 36 is 6, so you get your 6 square roots of 3. Okay, that's kind of like the shortcut. However, we're not always good at that, right? So this should be the most confusing one, because let's face it, whenever you show every single step and tell every single reason why, then it makes for a longer problem, right? So let's do 147. So 147 will divide by 7. So 7 and 21. And 21 is 7 and 3. So I have 2 of the 7s, and I have a 3. So is 7 squared a perfect square? Yes. And I know that because the exponent is divisible by 2, right? But 3 to the first power, that's a prime number, correct? And here's the thing. You don't want anything left under the root that has a power bigger than your root number. So if I already have a power less than my root number, then I already know this is going to be the number under the root. So I've got the square root of 7 squared and the square root of 3. What is the square root of 7 squared? 7. And then you have your square root of 3, which is your prime number there at the back. So 24. 24 is 2 times 12. 2 is prime. 12 is 2 times 6. 2 is prime. And 6 is 2 times 3, both of which are prime. So I have 2 to the third, and then I have this 1, 3. Now, is 3 going to divide by the 2? No, so I know I'm going to have to split that up into 2 different things. So really all I'm going to do is I'm going to knock one number off of this, because then that gives me the closest even number, right? So I have 2 to the second, and then one of these 2's is going to stay under the root with this prime number, right? Because it has a power of 1. So I'll multiply those under my root. What's the square root of 2 squared? 2. And then multiply your 2 and 3 under the root, which gives you 6. And it's okay to leave a number that's not prime under the root as long as it is the product of 2 prime numbers. Like 6 is made up of 2 prime numbers, 2 and 3. So that would be fine. All right, on number 4, that negative just chills all the way down. So you just kind of ignore it. Just stick it out front and let it be. So 80, we've got 2 times 40. 40 is 2 times 20. 20 is 2 times 10. And 10 is 2 times 5. So that gives me 1, 2, 3, 4 of the 2's, and then a 5. So is this a perfect square, this 2 to the 4th? Yes, because 4 will divide by 2, right? But this 5 to the 1st, is that a perfect square? No. And am I going to be able to do anything with that? No, because the power is smaller than my root number, which is 2, right? So I've got the square root of 2 to the 4th times the square root of 5. So I'm going to take that number up there, the exponent, I'm going to divide it by 2. So this will be 2 to the second, right? Because 4 divided by 2 is 2. Don't forget you still have your negative out front. And then this 5 is just following me down. 2 squared is 4. So I have 4 square roots of 5. Okay, 75. You could do 3 and 25. If you're thinking about money. And then 25 is 5 and 5. So I have 5 to the second power, and then a 3. Is 5 squared a perfect square? Yes, but 3 to the first is just going to be your prime number that stays, right? So I've got the square root of 5 squared and the square root of 3. The square root of 5 squared is 5, and then you have your square root of 3 at the back. All right, 96. 96. We can split 96 into 3 and 32. 32. We could do 2 and 16. 16 we could do 2 times 8. 8 we could do 2 and 4. And 4 we can do 2 and 2. So that gives us 1, 2, 3, 4, 2 to the 5th, and then a 3. So we already know 2 to the 5th is a no-go, right? 5 is not going to divide by 2. So we're going to shave 1 off of that, which would give us 2 to the 4th. And then what's going to be at the back that will stay under the root? 1 of the 2's and that 3, right? So the square root of 2 to the 4th would be 2 to the 2nd, which is 4, and then multiply the 2 and the 3 to make your 6. All right, so I kind of like to do the number and then do the variable and then just smash them back together. So I know that 9's a perfect square, so I'm not going to make you do a factor tree for that because it's already perfect. And then x to the 3rd, is that a perfect square? No, so how many of them do I need to make the perfect square? 2 of them, right? Which means that I'm going to have 1 left over. So they work just like your numbers do, right? So the square root of 9 is 3. The square root of x squared is x, and then you have your prime at the back. Okay. 25 is a perfect square, so we won't do a factor tree for that. But is x to the 5th a perfect square? No. So how many of those x's will I use to make the perfect square? 4 of them. Just shave 1 off, right? Which leaves how many left? The 1. There should always just be 1 left, right? Because, I mean, if you have 2, then you could square root that. So the square root of 25 is 5. The square root of x to the 4th, x to the 2nd, and then your square root of x at the back. Okay, I know we already did 75. We're going to do it again just for kicks and giggles. So I could do 3 and 25, and then the 5 and 5, right? So I get 5 to the 2nd and a 3, correct? So this is a perfect square, but this is my prime number, correct? And is this a perfect square? No. So we're going to have to split that one off. So I've got 5 squared, and I kind of like to put my perfect squares next to each other. So how many of these am I going to need to make the perfect? 4 of them, which means what's going to be left under the root in the end? One of these ends and the 3. So I'm going to put 3 in under there. So the square root of 5 squared is 5. The square root of n to the 4th is n to the 2nd, and then you have the 3 and your leftover n underneath. Okay. 162. So we can take 162 and divide that by 2, and that gives us 81. And 81 is 9 and 9. Well, 81 is a perfect square, right? Oh, why am I circling that? 9 is 3 and 3, right? So we're going to end up with 4 of those, right? Okay, so I have 3 to the 4th and a 2. So if I look at this, this is a perfect square, right? And this will be what's left underneath. Is this a perfect square? The x to the 4th? Yes. So I've got 3 to the 4th, and then I'm going to go ahead and put my x to the 4th up front too, because I like to have my perfect squares up front. And then what's going to be in the one at the back? 2. So I take the square root of 3 to the 4th would be 3 to the 2nd, which is 9. The square root of x to the 4th is x to the 2nd, and then you have your square root of 2. Okay, 180. That would be 2 and 90. 90 is 2 and 45. 45 is 5 and 9. Ooh, we're going to get 3 different numbers here. And 3 and 3. So we have a 2 squared, a 3 squared, and a 5. So both of these are perfect, yes. This is your prime number that's going to stay underneath. What about the x to the 9th? Okay, we're going to have to split that one up, right? So I have 2 to the 2nd and 3 to the 2nd. And then how many of these x's are going to make my perfect? 8 of them. So what is going to be left underneath back here? A 5 and an x. Alright, so I have the square root of 2 squared is 2 times the square root of 3 squared is 3 times the square root of x to the 8th, x to the 4th, and then you still have your square root of 5x, right? And then all you got to do is just multiply the 2 and the 3. That makes 6x to the 4th times the square root of 5x. And then number 12, 36 is a perfect square, right? And what about x squared? Okay, so we square root them both, and that gives us 6x. Okay, so when we divide a fraction, we can split that into the square root of the square root of the top and the square root of the bottom. Okay, so like I could do the square root of 15 over the square root of 64 and vice versa. Okay, so I never ever want to end up with a root left in the bottom, because then I've got to do what we call rationalizing the denominator, which you did in Algebra 1, but we're going to, be going over that again. So I'm not giving you any that aren't going to fully simplify out on the bottom, okay? So here's the thing. I'm going to look at this and say, okay, square root of 15. That's 5 and 3, right? If I try to do a factor tree for that, I don't have anything that's going to give me more than one of it, right? So I can't do anything with that, so I'm going to leave that alone. But the square root of 64 is 8, and I'm done. Okay, so 14, same thing, square root your top and square root your bottom, and both of these are perfect squares, so the square root of 81 is 9, and the square root of x squared is x, and you're done. So on 15, I square root the 11. 11 is what kind of number? It's prime, right? I can't split that. So it's going to stay the square root of 11, but the square root of 36 is 6. Right. So if I do the same thing here, what's the square root of 144? And the square root of n squared is n. Square root of 36, square root of z squared, square root of 4x squared, square root of 64, but then you're going to have to reduce, which just gives you x over 4. Okay, I'm going to add a couple to this. So let's say, for instance, that that number on the bottom, go ahead and write this one down, the number on the bottom is not a perfect square, right? But remember that if I'm square rooting the top and I'm square rooting the bottom, I can still reduce those because both of those numbers are under a square root, right? So it would help me if I did that. What do these both divide by? 3. So if I divide the top one by 3, that gives me a 5. And if I divide the bottom one by 3, that gives me 1. What do we know about the square root of 5? Can we do anything with that? No, so that's square root of 5. And then on the bottom, what's the square root of 1? And then I'm not going to leave that over 1. I'm just going to say that's the square root of 5. So if you can't just square root it, right, then go ahead and reduce it. Okay? Okay. So if you're looking at this, no wait, this is not the one I want to do. Okay, this is better. Alright, so if we look at this, $50 is not a perfect square, right? But I can reduce 6 and 50. They both reduce by 2. So if I reduce by 2, that leaves me with the square root of 3 on top and the square root of 25 on the bottom, which is a perfect square, correct? So square root of 3 stays on top because that's a prime number and I can't reduce that. And then the square root of 25 is 5, and then I'm done with that one.